Hello everyone, welcome to Understanding Physics, in which I will try to guide you through understanding physics. So today on Foundational Mathematics, we will discuss about differential calculus of one variable. So before we get started, I will briefly discuss each of the subsections for you to skip through later on. So if you want more of if you want more of these kinds of videos, please consider subscribing as well as liking, and also click on the notification bell to get the quickest update of the upload on this channel. So on differential calculus of one variable, we will later discuss about the core of differential calculus, in which we will discuss about functions first, and then continuity, and then after that we will discuss a little bit about what does it mean a function is what is the derivative of a function truly actually means. So with all of those definitions, we will later see some of the formulas for derivatives as well as the rules. The second will be about exponentials and log functions, in which we will discuss about the definition of the exponential as well as the log function, and we will basically also define what E truly is. After that, we will later discuss about trigonometric functions, in which we'll basically try to discuss about how do you get the derivative of sine to be cosine and vice versa, or like a negative sign for cosine. The next one would be about plotting functions, in which I'll try to guide you on how do you actually sketch a function by hand, which might be a little bit hard, especially if you don't know what the general features of the graph is. So this will be the best place for you to understand about functions itself. And so lastly, we will later discuss about differentials. So here are the timestamps for all of the subchapters that we'll later be discussing. So let's go and discuss about differential calculus. So let's talk about the very first subchapter, differential calculus. Differential calculus. So so first let's actually talk about what a function is. Because maybe you might have heard a lot about functions, but you don't really know the definition of a function. So the easy way for you to think about a function is that it is a machine. This machine you call as f of x. No, let's just call it f. And so if you put an input towards this machine, let's say x, it will output an f, which relates to x. So basically, this machine outputs an f that is worked on the value x. So it takes x, it does something to it, and then it outputs f of x. And this machine could be very arbitrary. It could be something like logic or 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 sometimes even algebraic equations that you use. And so that's basically the definition of a function. So one example is, for example, if the function is, for example, x squared plus 4, let's say. So if I put in the value 3, it will later output the value to be 9, which is 13. Is that correct? Yeah. So basically that's the definition of a function. And so anyways, You could say f to be g, h, I, j, k, or whatsoever, as long as it is conventional for you to use, as well as the x. It could be x, y, z, t, w, and etc. So this is basically what a function is. And so what does it mean for a function to be continuous? So I think the basic understanding of continuity is that you can draw the graph without even lifting your hand. And this is actually true, but in mathematics you need a much more better definition of this. So let's actually think about the definition of of a continuous function. So if I have fx to be a function, that is fx, so assume fx, assume a function fx, assume a function fx is continuous, meaning for every epsilon greater than 0, no sorry, for all epsilon greater than 0, which is in which for epsilon, for very small epsilon, there exists a delta greater than 0 such that the following thing exists: the function x minus the function of a, so yeah, it is continuous at a, sorry, at a. So fx minus fa, if you take the absolute value, it would be smaller than epsilon. For function of, no sorry, for x minus a to be less than delta. So what exactly does this mean? Well, if you look at this straight away, this might seem a very mathematics font, in which there's epsilon, there's delta. So what does it actually mean? So let's actually think of something like this. Let's just say I have a continuous function, something like that. And so let's say I have this point A. This would be, okay, let me just use a different color. Let's say this point here is A, and the value is f of A. So now let's actually set an epsilon. So epsilon is a very small object. So let's just say that the epsilon would be somewhere like that, I would say. So it will just basically box in the range of your function, or like your error. And so the question is, you could always find a delta such that, so yeah, this guy means that the range from here to here is something which you would call as a delta. So this is epsilon, that's delta, that's delta. So something like that. So if I box this in correctly, you would see that there should exist a delta such that the value is still in between these epsilons. So let's do something like this. And so if I state this as A, you could you could go ahead and create a box. Nope, let's just actually use this. So we could create a very small boundary. This is for any epsilon. You could still create a boundary such that your function here doesn't exceed the epsilon that you have already chosen. And this works for any epsilon as long as the epsilon is very small. And that's the definition of a continuous function. Well, let's think of a non-continuous function. Let's say something like that. And I want to check the value. Okay, so let me just let this guy to be open and this one to be a closed one. So let's just check this value here. If you actually set an epsilon to be lower than this range, delta does not exist. Delta does not exist, DNE. So this means that the function itself is not continuous. So there's a jump between the value. That's basically the definition of a continuous function. So after we have already talked about a continuous function, we should now discuss about the derivative of a function. So what do we call so what is the derivative exactly? So this is like a multiplication, addition, subtraction. Basically, it is a function. So derivative is a function. So that if you have x, you put it inside this box. You take the derivative. It will transform it into, oh wait, let's just give that fx. It will turn it into df over dx. So what's this? So df over dx, or sometimes you could write it as df sometimes, or like a dx of f, something like that. This is basically the limit as delta x goes to 0 when function x plus delta x minus function x over delta x. So this is basically the definition of a derivative. Well, if you actually analyze this much more further, you could state that this is the gradient of a function. Well, it is the instantaneous gradient. And thinking about this further, if you have already looked at General Physics 1, this is very similar to the instantaneous velocity of a moving object, especially in one dimension. So this is the definition of a derivative. So let's just give an example. Well, let's just so we will just assume that we have x to the power of n. We will just state that. And so what's the derivative? So what is the dx to the power of n? That's the question. So to do this, we could straight away just look up the definition straight away. So it's the limit as delta x goes to 0. Oh yes, anyways, I'm gonna assume n to be a part of the natural number. Something like 1, 2, 3, and so on. Well, I could also define the thing to be 0 as well, but I will let 0 to be its its other thing. As like, yeah, it could be a practice for you to figure out what the answer is for x to the power of 0 is. So for x to the power of n, we would have x plus delta x to the power of n minus x to the power of n divided by delta x. So what after this? Well, let's try to open this up. So we could get x to the power of n plus, so anyways, if you see here, this is basically x plus delta x multiplied n times. This is n times. And so how many combinations can you create x to the power of n minus 1 and delta x, meaning that you will leave out one of the x? Well, if you actually look at the entire array, you just need to miss one of them, and it could be any of them. It could be the first one, second one, third one, and so on. So that means there is n different combinations. And so if you actually do this for all of the power of n's, I will just call this the r delta x squared, in which r is a function. So that's basically the x plus delta x to the power of n, subtracted by x to the power of n, divide everything by delta x. You take the limit as delta x goes to 0. You would observe that this delta x to the power of n could cancel each other out, so you would get the limit as delta x goes to 0, and if you see here, this is n x to the power of n minus 1 plus r delta x. So when delta x goes to 0, this r times delta x would also go to 0. So you would get n x to the power of n minus 1. So this law could work for any natural number. But you might know that it will work for the whole powers. I mean the n could be a real number as well. But we won't really discuss about that until we have already discussed about exponentials, since in here we are only able to define what is the power of a natural number. And if you actually think about, if it is a power of 0, that means that it would mean that the function is basically 1. So it's basically 1 minus 1, which is 0 over delta x. So like, yeah, it is like 0 over delta x, but then like, yeah, obviously 0 divided by delta x should be 0 anyways. So therefore the derivative will be 0. So that's something for you to think about. And so I want to introduce this denotation for derivatives. So I will write derivatives as d to the basis sometimes x, or like, yeah, sometimes I could just write this as like d, and then there will be a power here, which basically corresponds to how many times do I do the derivative with. So that's the way that I will write derivatives in here. So now I want to discuss about the linearity of the differential operator. So let's just state that, so for a linear function, which is a fx plus b gx, this would mean that the derivative would be a df plus b dg. But why is this the case? So let's think of this as the limit again. The limit as delta x goes to 0 of this entire function, but then x plus delta x. So it's a fx plus delta x plus b gx plus delta x. So yeah, these two are functions. Subtract that by afx plus bgx. And let's divide everything by delta x. So what do you observe here? Well, we can just group the a's. So the limit as delta x goes to 0. So we can group all of the a's together. So we'll get fx plus delta x minus fx. And the b, we can group them together. Gx plus delta x. Let's go to the side a little bit. Minus gx. Divide everything by delta x. So we could rewrite this as the limit as delta x goes to 0 of a function x plus delta x minus fx, this entire thing divided by delta x, plus the limit as delta x goes to 0 of b gx plus delta x minus gx over delta x. You would see something. This a here this a and the b could go out because it doesn't truly it is not influenced by the delta x, so it is fine for us to bring it outside. And so another thing is that you need to look at this entire thing. This entire thing here is basically the definition of a derivative, df as well as dg. So that's the proof of this linearity of the differential operator. So after this, you would also think about what if I multiply two functions together. So yes, anyways, the top one will basically solve almost any polynomial, regardless of like the size. It could be x to the power 4 plus something x to the power 3, and basically you could just use this power of the linearity of derivatives as well as the definition that we got earlier. So what about if we multiply two different functions together? So let's think about this. The d of f times g. Well, something for us to think about is that we could just straight away use the definition straight away. That's fine. Function x plus delta x, gx plus delta x minus fx gx over delta x. So let's see here. I can't truly separate these two things out straight away, but maybe I can do something. Maybe I can just transform this fx plus delta x gx plus delta x, subtract that by another function. Let's just state that to be function x gx plus delta x. But in doing so, I must to keep this equation in balance. So that means I need to add fx gx plus delta x as well. So you might think that this doesn't truly help anything. But if we actually observe these two as well as these two, we can start to actually separate the variables or separate the functions. So we'd get delta x going to 0 of this first part, which is gx plus delta x of this entire function, fx plus delta x minus fx there. And let's just actually divide everything by delta x straight away here. And we can add that with this other one. So it will be function x going outside. We observe gx plus delta x. And then minus g of x. Divide everything by delta x. Well, basically only this part. So, like last time, we will basically split this limit into two. So this will also be the limit of as delta x goes to 0. And here's something for you to observe as well. We do know that this right-hand side, I mean, it could be infinity, it could be 0, but yeah, as long as gx plus delta x doesn't also exhibit those kinds of properties, we could just actually separate them both. It is not as if it is 0 over 0 or infinity over infinity. So we could just write this gx plus delta x straight away out. So that's g of x, which I'll just write that as g. And you would have df, which is the derivative. And, oh, let me just edit that. So it's g df. And so you could add it with the f, which doesn't have this delta x, and this gx plus delta x minus gx over delta x. That's the definition of the derivative. So this is one of the formulas that you might have already learned in high school, for example. But now you know where it actually comes from. So if this is the first time of you saying this rule, it is very useful, especially if you are doing multiplication. So for example, if I have x plus 2 squared times x plus 3 cubed, you could just use this to find the derivative straight away, instead of opening up the brackets and multiplying them all together. So that's for the product rule. And so now I want to discuss about the chain rule. So so the chain rule basically tells you that it's the df of u of x. So you could see that there's a function inside a function. So how do you solve this again? Well, we could just straight away use the definition again. So it will be f of u x plus delta x minus f of u of x. Divide that by the delta x, right? But let's do a trick. Let's just multiply the top and bottom by ux plus delta x minus ux. Divide that by ux plus delta x minus u of x. So now we could just transform this a little bit. The limit as delta x goes to 0 of function u plus delta u minus f of u, divide that by the delta u, multiply that by ux plus delta x minus u of x, divide that by the delta x. So you could see the delta u itself is the definition that if you add the subtle change in x, it will cause the delta u. And so this principle also works for the function f, because we are changing the small thing in the delta u. So it will also influence the f of u. So looking at this now, we could just separate both of the limits as both of them both of them don't have the 0 over 0 or the infinity over infinity, let's say. So we could get this guy, this front part, to be df over du, multiply that by du over dx. Or sometimes I could write this as the du of f, multiply that by the dx of u. But this notation might be a little bit confusing. So instead, you could actually just see this one straight away. So it is as if you multiply top and bottom by du and separating them both. So that's what you call as the chain rule. So after this, I am gonna try to discuss of one of the formulas that you could gain from both of those, as well as a single definition of a derivative. So let's consider this following derivative, the dx inverse. This doesn't seem to be a hard one because you could actually use the formula straight away, right? Well, last time I discussed that it has to be a natural number. So we don't know how to do this, right? So let's think about this straight away. So the d of x inverse could be written as the limit as delta x goes to 0, right? So it will be 1 over x plus delta x minus 1 over x, divide that by delta x. So let's just make the top one to have the same denominator. So this will be x minus x plus delta x divided by x times x plus delta x, and then you would need to multiply this by delta x again, right? So this will later result in a negative number at the top. This will be negative 1. So this would mean that it will be the limit as delta x goes to 0 of negative 1 over x times x plus delta x. So as delta x goes to 0, this would mean this will be 1 over x squared. So that's the derivative of the 1 over x. So with this, we should be able to define what is the df over g. So let's try to do this. So first, we observe that we could actually do d of f times 1 over g, in which we already have the formula. So we could write this as 1 over g df plus f d 1 over g. So what's this derivative of 1 over g now? Well, this derivative is with respect to x, let's say. So we can't truly ascertain that straight away, but we can do something. So let's just assume this to be h. H is 1 over g. Okay. So what happens with that? So if I do the dh, this would basically mean this is dh over dx. Well, what if I write this as this? dh over dg times dg over dx. Now you would see something. Now since the h is 1 over g, and you would differentiate this with respect to g, you would get this negative 1 over g squared, right? And multiply that by the derivative of g with respect to x. So this is what you get. Negative 1 over g squared dxg. So you could rewrite this as, oh wait, there, where's my f? There. So if you actually make the bottom one to be the same, it would be g dx f minus f dx g over g squared. This is the formula for quotients. So if you have one function divided by another function, you could use this formula to find out what is the derivative. So something that could be useful is to observe that df over dx times dx over df would be the same thing as 1. Well, you could say it straight away. So now we could actually start to think about some of the reciprocals as well. But we cannot really define what does it mean to take a power of a rational number. So take something like this. Y is x to the power 1 over 2. Well, I still don't know what does x to the power 1 over 2 is. but I know that if I square them both, I'd get y squared equals to x. So this might be something interesting. So let's take the derivative of y with respect to x. So the first thing that you would see, this is dy over dx, right? Well, what if I only discovered the dy over x? This is much more easier. You could just use the formula straight away. Y squared, the dy of y squared. So this would mean the n would be 2 times y to the 2 minus 1. This would mean this is 2y. So because we know that dy over dx, so this is dx over dy, times dx over dy is 1, and this guy is 2y, therefore we know dy over dx is 1 over 2y. And that's the definition when you take the derivative of a rational number. But this might be a very hard process for you to do every single time. So what if we will try to define what is the power of a rational number is? Or even better, we should try to define the power of a irrational number. So let's go and do that in this next subchapter. So we have already figured out the definition of x to the power of n when n is a natural number. And so now I want to ask a very important question. What is x to the power of p when p is an element of the real number? Well, this might be a little bit complex, so instead of doing this straight away, let's just tackle a simple problem. I will just try to figure out what's the x to the power p if p is an element of the z first. So one way for you to do this is that if you actually write x to the power of m multiplied by x to the power of n, this basically means that you would have multiplications of x of m times, multiply that by the multiplication of x n times. So basically, in total, you would have m plus n. So therefore, you could conclude that x to the power of m plus n is the same as x to the power of m times x to the power of n. So let's just use this definition to figure out what's the power of a negative value. So if you actually try to plug in, let's just state that I'm trying to figure out what's x to the power of negative 2. So we know for a fact that x squared multiplied that by x to the power of negative 2 should be x to the power of 0, which means that the value should be 1, right? So with this, we could just actually state that basically this guy here is 1 over x squared. It's pretty much logical that you could cross out the x squares to get your 1. So that's the definition of negative power. It means that you do 1 over x to the power of this value. And so maybe we should actually try to figure out what is the definition when the derivative of x to the power of negative of m truly is, when m is an element of the natural number. So let's try to solve this straight away. So the method that I'm going to be using is that we will actually just turn this into d to the power of 1 over x to the power of m. So that means that we could actually use the quotient rule. So it's the derivative of the top one, multiply that by the bottom one, that's x to the power of m, and the derivative would be 0. So the value doesn't exist. No, sorry, the value is 0. But you subtract that by this value, multiply that by the derivative of the bottom value, which is m to the power of xm minus 1. Divide everything by x to the power of m squared, the bottom one squared. So this would obtain negative m to the power of x, and that's 2m, right? So m minus 1 subtracted by 2m, you would get negative m minus 1. So this is pretty much the same thing that you saw previously. So therefore, I could also conclude that if p is an element of z, the derivative of x to the power of p would be px to the power of p minus 1. So we have proved this as well for negative powers. But what about if my value is a rational number? Now, we need to start thinking more about what is the definition when x is to the power of this value q. No, sorry, a power of a rational number. So let's think about this again. I'll just state that I have a value, x to the power 1 over m. I need to, so something that you could see here is that if I want this guy to be 1, that means I need to multiply this guy by m times, right? So this means that it's x to the power 1 over m to the power of m. So basically, this means that this is the value. No, sorry, this should be x. So this logic states that this number, which could be which is a number, that if you power it by m, would give you the value inside the number that you're powering in. So that's something to realize, is that we start to define the number related to the x to the power 1 over m. So if we also do the derivative of this, the d of x to the power 1 over m, it will be pretty similar to the one that we did previously here. So let's just assume that x to the power 1 over m is y. So let's just do the dy of x, since we know y to the power of m will be x. So this would be m y to the power m minus 1. So the dxy, the dx, the derivative of y over x, would be 1 over m y to the power of m minus 1. And this is basically 1 over m, multiply that by x 1 minus 1 over m. It makes sense. And we can just put this guy upwards, so we would get x1 over m minus 1 over m. So we got this relation. So we have fully understand the concept of the power of a number with the power to be a rational number. But we haven't truly fully understand the whole rational number. Instead, we only look at 1 over m, where m is a natural number. So with that, we should actually try to think of this type of polynomial. Let's state x to the power of p over q. Looking at this straight away, we do see that we could separate this into x to the power 1 over q to the power of p. So with this, if we actually take the derivative of x to the power p over q, we would get d x1 over q to the power of p. So one method for us to solve this is by using the chain rule itself. So let's use the chain rule straight away. So we would obtain p d x1 over q to the power of p minus 1. And so now we need to find the derivative of x to the power of 1 over q, which we have already figured that out to be 1 over q, x to the power of 1 over q minus 1. So combining this whole thing together, sorry, there shouldn't be any derivative there. It would be p over q, x to the power of p over q minus 1 over q. Multiply that by x1 over q minus 1. We do see that this 1 over q could be cancelled out with each other. So we would obtain p over q, x to the power p over q minus 1. So this is basically the formula that we have already obtained from the previous computations as well as proofs that we did. So for any rational number, n is an element of the rational number, we would obtain x to the power of n. The derivative would always be nxn minus 1. So we have fully understand what is the definition of x to the power of a rational number. So what about x to the power of a real number? So if we state x to the power of n when n is a real number, instead of that, we'll actually just try to consider a to the power of x, where x could be any value, because it encapsulates from the rational numbers all the way towards the irrational numbers as well. So if we try to figure out what the delta a to the power of x is, this is ax plus delta x minus a to the power of x. We do see that we could actually write this down as a to the power of x with a to the power of delta x minus 1. So if we try to approach delta x going to 0, we do see that the inside here, when delta x goes to 0, it would be a number very close to 1 plus something to times the delta x, in which we'll just call this as the natural log of a, and etc. minus 1. So this is basically the Taylor series of a to the power of delta x when delta x goes to 0. But we haven't truly understand what is this function natural log of a. But if we actually try to compute this into our derivative, we would get the derivative of a to the power of x with respect to x will be you could cancel those. So it would be natural log of a, multiply that by a to the power of x. So that's the definition of the derivative of a to the power of x with respect to x. And so this natural logarithm is something that we don't fully understand a lot, but we can actually try to analyze it by giving it certain values. So if we analyze 2 to the power of 0.01 and 3 to the power of 0.01, we do see certain things. First of all, that this value inside here would be 1 plus natural log of 2, multiply that by 0.01, and the other one is 1 plus natural log of 3 times 0.01. If you multiply these two numbers, if you take the power of each to the power of 100, they should be about 2 or 3. And so, observing this, we do see that the natural log must increase monotonically, so it always goes up. And also another thing to see is that if you put 1 into the equation, it's basically as it is d of x 1 to the power of x, which is the same thing as 1. So it's d over x of 1, which is 0. And this has to be the natural log of 1 times 1 to the power of x, which is 1 as well. Therefore, natural log of 1 has to be 0. So with this logic itself, you do see that when the value is above 1, when a goes above 1, it has to be a positive number. And not only that, it must always increase. But compare that if you actually take a smaller number. Let's state something like 0.99. If you do the same thing as the above, you do see that the value goes negative, and it has to go very down into the negatives. So when a is less than 1, the value is negative. And in fact, the natural log is only defined from a value above 0, not 0 itself. So these are the only clues that we can gain in order to graph the natural logarithm, which could be something like that, we don't know, or something like that, or many other ways for you to graph the natural log. But we will actually try to figure this out by actually figuring out one value such that the natural log of this value e is 1. So we'll just define this value to be e itself. We don't know what the value of e truly is. So if you take the derivative of e to the power of x, it should be the natural log of e times e to the power of x, which is e to the power of x itself. So this gives us a clue in the Taylor series. So with this interesting property of the e to the power of x, we are able to figure out that we could actually do the approximation for e to the power of x itself when x equals to 0. So let's just do that straight away. If we actually figure out what e to the power of x is, it's basically equal to 1 plus x squared over 2 plus x to the power 3 over 6, and so on. So basically the Taylor series tells you the approximation of the slope during this certain point. In this case, it's x equals to 0. So with this, we could just write this down as the sum of x to the power of n over n factorial when n goes from 0 towards infinity. So that's basically the definition of e to the power of x. So does this always work for any single value of x? Because this is just an approximation. Well, we could just look at the convergence of the series itself. So the way that we will look at the radius of convergence is by using the ratio test, which is one of the tests that is normally used when determining a series is convergent or divergent, which we will later discuss on a future video. So the ratio test tells us that the limit as n goes to infinity of the absolute value of the an plus 1, which is 1 over n plus 1 factorial, multiply that by x to the power n plus 1, divide that by the an, which is 1 over n factorial, multiply that by x to the power of n. So we could cross this out to obtain x there, and so we would obtain it's the absolute value x over n plus 1, and this has to be less than 0 for it to converge. So the radius of convergence tells you how far can you go from x such that this value is always convergent. And so for this value, even if I choose a very big number, I could always choose an n much more bigger than this value, such that the value is less than 1. So I can conclude that the radius of convergence is infinity. So therefore, this works from negative infinity to infinity for e to the power of x. So this definition could be used for our definition of e to the power of x. So if you actually do the numerical computation of e to the power of 1, which is basically e, you would get this value to be about 2. Let's see here. It's about 2.7183 and some other value. So another interesting thing to describe e to the power of x is by using a very interesting limit. The limit, no, sorry. So we'll just define e of n comma m to the power of x, which equals to 1 plus x over n to the power of m. So if you actually try to find certain values when n or m goes to infinity, you would see certain values of this en comma m to the power of x. So one value is if you actually set n going to infinity, keeping m fixed, you would get the value to be 1, because this value will no longer exist, so you would only have 1 to the power of m. But if you do m going to infinity and n is fixed, it depends on your choice of the x as well as the n. The value of the inside could be bigger than 1, which means it will be infinity, or if the x over n results in a negative value, it could go towards 1. No, towards 0. But what if I state that the n equals to m, or the en of x is 1 plus x over n to the power of n, and trying to find when n goes to infinity? Well, let's try to take the derivative with respect to x of this e to the power of nx. We do see that by using the rules, such as the chain rule as well as the rules for polynomials, we get n 1 plus x over n to the power of n minus 1. Multiply that by the derivative of the inside, which is 1 over n. Crossing that out, we would get 1 plus x over n to the power of n over 1 plus x over n, the limit as n goes to infinity. So looking at this now, we do see that the top side is en to the power of x, while the bottom one is going towards 1. So this is the definition of enx, which is basically ex, the limit as n goes to infinity. So this is something interesting for you to see, because this is basically what the banking industry always look at. If you take very small amount of time with a certain amount of your interest. So the shape will be somewhat like a e to the power of x curve, which goes something like that. So that's basically e to the power of something. And so with this, you could also define hyperbolic functions by using e to the power of x. So the first hyperbolic function is the sinh of x, which is defined to be e to the power of x minus e to the power of negative x over 2. And what about cos x? That's e to the power of x plus e to the power of negative x over 2. So there are multiple different identities that these two can cover. One of them is cos squared of x minus sinh squared of x is 1, while the other is the sinh of x plus y. The sinh of x plus y is the sinh of x cos of y plus the cos of x times the sinh of y. So it's like the property of a sign, and you could prove this by only taking the definition of the e to the power of x minus e to the power of negative x, and etc. So something also to take note is that cos is a even function, while sinh is a odd function. So let's now jump towards the definition of a to the power of x. So we last time did d8 to the power of x over dx is natural log of a times a to the power of x. And if you take the Taylor series itself, you would also get from 0 to infinity of natural log of a to the power of n no, sorry. Yeah. Natural log of a to the power of n, x to the power of n over n factorial. But this can also be written as x natural log of a, everything to the power of n, over n factorial, the sum of when n goes from 0 to infinity. And so this is the definition of e to the power of x natural log of a. So if you take x equals to 1, that means that, so this is a to the power of x. So if you take x equals to 1, you do see that a equals to e to the power of natural log of a. And this is an interesting fact. E to the power of something is the inverse of the natural log of x, and vice versa. So we can use this property to figure out what's the definition of x to the power of a later on. But now let's actually try to analyze what is the natural log, what's the derivative of the natural log of a. So the way that we'll actually do this is by actually taking the derivative with respect to a of this value here. This would mean it's 1, so 1 is equal to the derivative of a of natural log of a, multiply that by e to the power of natural log of a. So you would get the derivative of a natural log of a will be 1 over this guy, which is a itself. And that's literally the definition of the natural log of a. And if you extend this further, you would see that the derivative with respect to a n times the nth derivative with respect to a of natural log of a will be negative 1 n plus 1 and minus 1 factorial. Divide that by a to the power of n. So you can compute this straight away just by doing multiple derivatives. And so if you try to do the Taylor series, well, we cannot truly do the Taylor series at 0. So let's do that when a is 1. So you would get the sum when n equals to 0 towards infinity of negative 1 n plus 1 over a to the power of n. No, sorry. It's when a equals to 1, so we don't need to care. So the bottom side there will only be an n. Multiply that by the x minus 1. Sorry, this should be a minus 1 to the power of n. So basically the natural log of x could be written as the sum when n equals to 0 towards infinity of minus 1 n plus 1 over n x minus 1 to the power of n. So let's just call this x minus 1 to be y. And let's try to figure out the radius of convergence of y to see where would the number converge if you actually do this Taylor series. So let's do the ratio test again. The ratio test reveals us that it will be negative 1 n plus 2 over n plus 1 x minus 1, no, sorry, that's y to the power of n plus 1. Divide that by the negative 1 n plus 1, divide that by n, y to the power of n. We can cancel out the y to the power of n, so we'll get only y, and we could cross these out to get the negative 1 on the outside. So we would get, so this is the absolute value, the limit as n goes to infinity. So we would obtain negative y n over n plus 1. So you would take the absolute value of that. So here's something interesting to see. N over n plus 1. And this value must be less than 1. There are only certain numbers that could fulfill this limit. So if you take this limit as n goes to infinity, this value goes near 1. It's basically like infinity divided by infinity, but they all go at the same pace. So it should be around 1. So therefore, you would figure out that the radius of convergence is 1. But then that means that the series here only converge starting from 0 until 2. So what about other values other than from 0 to 2? Well, first of all, let's think of this more carefully. Obviously, you couldn't have the natural log of 0, because that means 0 to the power of something. No, sorry. 0 0 to the power of something has to be e, let's say. That's basically the definition of the natural log of 0 is x. So looking at this, there couldn't be a value such that this exists, but this could work with numbers like 0.1 or other values. That means that the x should be negative infinity. But in here, 0 couldn't work. And the same idea goes towards negative numbers as well. But what about values above 2? Because we know that natural log of 3 exists. And that's where we will actually use the definition of powers again. So remember the properties of powers. If I have a as well as b, I could state a is natural log of a, e to the power of natural log of a, and b is e to the power of natural log of b. Making sure that both numbers are positive and also smaller than 2, while also a positive number. If you actually add these two guys together, multiply them both together, you would get e to the power of natural log of a plus the natural log of b. So you would obtain that the natural log of a times b, so you could write this again as e to the power of natural log of a times b, therefore you would get the natural log of a times b is equal to the natural log of a plus the natural log of b. So we could create numbers above 2 just by doing multiplications of numbers. So you could extend your curve all the way towards infinity if you multiply the right numbers. So there are other ways for you to write logarithms. So the one that we have already written is something which we call as the natural logarithm, as we have already said before. But what about if I want the base, not e, but instead we'll just call that to be b, or let's just call it b. So let's say I want to define the value of the the logarithm of b. So basically, is a, that means that it's b to the power of a is x. So this could be useful. So let's figure this out. Let's try to define x is basically e to the power natural log of x, which basically is b log b y. No, log of subscript b of y. So you could write this log of b here to be e to the power of natural log of b and multiply that by the log b y. So you could now convert the natural log into any type of logarithms that you want. You could even create values which are not even whole numbers as well. So this would be the the log b, oh wait, there's some change in the variables. So it's log b of x is the same thing as the natural log of x over the natural log of b. So this works like a conversion factor. If you want to convert the logarithm, the natural logarithm into logarithm, there is this conversion factor of natural log of 10. So the logarithm base 10 will tell you a lot about decibels. It is where the definition of decibels comes in. It's the logarithm base 10 of the sound intensity. So that's where it is applied in your life. So now let's go and jump in towards the definition that we really want to figure out. What is x to the power of p when p is a real number? So we can now do this. We can just change x to be e to the power of natural log of x times p. And if we take the derivative, there. So we can write this as e to the power of p natural log of x, multiply that by the derivative of the power here, which we know to be p over x. So therefore, we figured out p, multiply that by this guy here, which is x to the power of p as well. So we can write that, divide that by x. We would get px to the power of p minus 1. And this is the definition which we have already covered for all rational numbers as well. So in fact, this formula here could also work for the real numbers as well. So we can now develop the binomial theorem not only for natural numbers, but also for real numbers as well. So we can write this as the sum. No, let's just actually write this down. So the binomial theorem could now be written as 1 plus px plus p times p minus 1 of x squared over 2 factorial plus p times p minus 1, p minus 2 over 3 factorial times x to the power of 3. So we have now fully understand the definition of x to the power of p. So now let's think about the sinh as well as the cosh, as well as its inverse, while also trying to figure out what's the derivative of each of these values. So for sinh, it's e to the power of x minus e to the power of negative x over 2. If you actually try to find the derivative, it will be e to the power of x plus e to the power of negative x over 2. This is the cosh. And same logic goes for cosh, which is sinh. So that's an interesting fact for you to figure out with sinh and cosh, is that the derivative of sinh is cosh, the inverse of cosh is sinh. And what about the derivative of its inverse? Well, for the derivative of the arcsinh or the inverse sinh of x, we could just assume this to be y first. And so we would obtain sinh of y is x. Doing the derivative with respect to y, we would obtain cosh of y. And the cosh of y follows the rule. It's 1 plus sinh squared y. So therefore, I could just write this as the square root of 1 plus x squared, which is the dyx. So because of the inverse relation, we do figure out that the inverse of the derivative of y with respect to x is 1 over the square root of 1 plus x squared. Let's try to do this as well for the cosh. So let's assume that to be y. We would obtain x equals to cosh y. And taking the derivative with respect to y, we would obtain sinh of y, which is equal to, so it's the square root of cosh squared y minus 1. This means that this is the square root of x squared minus 1. So the derivative of y with respect to x is 1 over the square root of x squared minus 1. So after we have discussed all of these things, maybe it is important for us to also try to figure out the definition of the sinh and the cosh by using Taylor series. So we know that the convergence of the Taylor series goes for any single value of x. So we can use that definition, but you could also do it by straightaway utilizing the definition of the Taylor series straight away. So if we analyze that to be at 0, so the sinh of 0 is 0, while the cosh of 0 is 1. So just by using this, we can develop that the Taylor series of sinh x is the sum from n equals to 0 to infinity of x to the power of 2n plus 1 over 2n plus 1 factorial. This basically means that this is all of the components which are odd. So you could see that this is an odd function because all of its powers are also odd. And compare that to cosh x, which is the sum infinity n equals to 0 of 2n factorial x to the power of 2n. So you could see that one of them contains all of the even number and the other one contains all of the odd numbers. And here's also something interesting. If you actually sum sinh x and cosh x together, you obtain the e to the power of x, which if you look at its Taylor series also matches up. And same thing is true if you actually do cosh x minus sinh x. You would get e to the power negative of x, in which its plus and minus also match up with the Taylor series of e to the power of negative x. So we have already figured out the Taylor series of sinh as well as cosh. So that's the whole thing about the logarithm as well as the exponential. So we have already finished discussing about exponential as well as logarithms. So now we want to start to develop this idea further into trigonometry. So first, to review about trigonometry, we will start by defining what is the sine as well as the cosine first. So there's sine A as well as cosine A. So this means for a triangle with this angle, there will be this hypotenuse as well as the adjacent and the opposite side of the angle A. So the opposite side means the side which is not touched by the angle, while the adjacent is the one that is touched by the angle. And then the hypotenuse is where it is the longest. So pretty much the way that you define sine and cosine is by using the right triangle. So the sine is defined to be the opposite over the area, while the cosine is the adjacent over the hypotenuse. Sorry, so that should be the hypotenuse. So with just this, we can actually develop the idea of trying to solve sine A plus B. So how do you define what sine A plus B is? So let's just actually use the straight definition straight away. So let's just state if I have two angles, A and B. So this is A, and then this one would be, no. Let's redraw this again. So let's say this is A and this is B. So the sine of A plus B could be drawn as something like this. So if I bring this up and then attach it, so this triangle here will represent the sine of A plus B. And so what sine B could be written as something like this, and then for sine A, it could be drawn as something like that. So, how do we solve for the height of this entire object? So the easy way to think about this is that we have this length as well as this length that we need to compute in order to find what is the opposite side of this sine a plus b. So it's pretty much the O over the h. So I'll just call this as h at this point. So h of sine a plus b must to be this total length. So this h sine a plus b is this length here as well as this length in here. So this first length here is pretty much it's the sine of a, multiply that by this length, which I'll call that as c first at this point. So we'll call that as c. So we got c times sine a. And then we need to add this by this other small length. So this other small length here can be figured out as long as you know what is the length of this thing here. So what's the length? So let's redraw this here. So we know that this should be a. And why is it? So if we actually draw this line here, you would see that this angle as well as this angle should be the same. Therefore, that one and that one should be the same because it is perpendicular to each of these lines. So we would get this triangle here. And this triangle here has this length here to be the thing that we are looking for. No, sorry. This is the one that we're looking for. And then this one we will just call that as b at this point. So we'll call that as b times the sine. Is it sine? No, it's the cosine. The cosine of a. So what's c and what's b? So the easiest way to do this is by actually dividing everything by h, because we don't truly need to know what c and b is, but we need to know what sine a plus b is. So therefore we could just write it like that. So sine a plus b equals to c over h. What's c over h? C over h is the cosine. It's the opposite over, it's the adjacent over the hypotenuse. So it's cosine. So it's sine a times cosine b plus the cosine a times what's the b? The b here is, no, sorry, so what's b over h? B over h is the opposite over hypotenuse. So that means this is sine b. And there you have it. That's sine a plus b. So that's the first thing for us to develop. And now the second thing that we want to develop is the limit of sine theta over theta. So let's do that. So the limit of theta going to 0 of sine theta over theta. So maybe you have already known this to be equal to 1. But how do you know that? But why is it the case? So we will just do this using the geometry. So let's state that if I have a sphere here, and then there's this guy, this angle here to be theta, which is very small, and then we could take several lines here. So this first line here, the one that I'll color in red, it is perpendicular to the horizontal line. The green one represents the one through the arc. And finally, the one in blue will represent the one that is going outwards. It is tangential to the circle. And so what we can actually observe from this is that the area of the one that is bounded by the red one must be smaller than the one bounded by the green, which also be smaller than the one in blue. So we could just write this down straight away. So for the red one, we should remember about the formula itself of the area of the triangle, which is half times the base times the height. So the base in here, the radius of the circle is r. So we are able to get the base to be r times cosine theta. So it's opposite over hypotenuse. Multiply that by the hypotenuse itself. So we would get the adjacent, and then we could multiply that by the opposite side. So it's opposite over hypotenuse, multiply that by the hypotenuse. And this value should be smaller than or equal to this small arc. And the easy way to represent this is by using theta over 2 pi times pi r squared. So this is pretty much the ratio of the area. So we could just write it like that. And then this is smaller than equal to the one in blue. So the one in blue has its base to be, so it's half times the base times the height. And here, the height would be the tangent of theta. So what's tangent? Tangent here is the sine over cosine, or the opposite over the adjacent. So we are pretty much multiplying the adjacent side by the opposite over adjacent, which is the same thing as the opposite side, which is the one in blue. So what we can do now is that we can multiply everything by 2 over r squared. So we are going to be obtaining sine theta cosine theta is less than equal to, so these guys cross each other out, that's theta, which is less than equal to tangent of theta. So what we can do now is that we can divide everything by sine theta. So we'd get cosine theta, which is less than equal to theta over sine theta, which is less than equal to 1 over cosine theta. So remember, tangent of theta is sine over cosine. So in here, what we observe here is that when theta goes to 0, the left side approaches to 1, the right side approaches to 1. So by the sandwich theorem, we are able to obtain that the limit of theta over sine theta is 1. And therefore, the sine theta over theta limit as the theta goes to 0 must also be 1. So that's the proof. So we have already found the limit of sine theta over theta, which is pretty close to 1. So now let's actually try to find the idea of cosine theta for pretty much small angles. So cosine theta has the property that the cosine squared theta plus sine squared theta is 1. So we could write cosine theta to be the square root of 1 minus sine squared theta. And so if you take small values, sine theta will be pretty much, so yeah, from here we could state that sine theta is pretty close to theta for small values. So we could almost write it as the square root of 1 minus theta squared. And using the binomial theorem, we could write this as 1 minus half theta squared plus some other stuff. So this only works for small thetas. But we do see that if you actually try to plug theta in, this would go to 1 first. So if you change it by a small amount of theta, the value will still be about 1. So with that, we can now start to find the derivative of sine. So the derivative of sine theta would be, so the change of sine theta first would be sine theta plus delta theta minus sine theta. So this would be sine theta cosine delta theta plus sine delta theta cosine theta minus sine theta. So when delta theta goes to 0, this pretty much goes to 1. So we could just cross this out in order to obtain sine delta theta cosine theta. And this is pretty close this is pretty close to delta theta. So we could just write it as this. So we have obtained the derivative of sine theta, which is the cosine theta. What about the derivative of cosine theta? Well, we could just do this just by using the rule from chain rule, or the rule from the inverse function. No, sorry. This will be the rule from the chain rule. So cosine theta can be written as the square root of 1 minus sine squared theta. So taking the derivative of this, we are able to obtain 1 over 2, so that's the half, and then there's 1 minus sine squared to the power of negative half. So that's the square root of 1 minus sine squared theta. And then we will multiply it by the derivative of the inside. So it's negative 2 sine theta cosine theta, because we have already figured out what's the derivative of sine theta. So this bottom side here turns out to be cosine theta as well. So we can cross these out to obtain that the derivative of cosine theta is negative sine theta. So with only these two derivatives, we are able to obtain the Taylor series of the sine as well as the cosine. So the derivative, so for the Taylor series of sine x, it is similar to the cosh, which is negative 1 to the power of n, x to the power of 2n plus 1 over 2n plus 1 factorial. And we can do the same thing for cosine. It's from 0 to infinity of negative 1 to the power of n, x to the power of 2 over n, to x to the power of 2n over 2n factorial. So this can be done just by using the definition of Taylor series. And by the way, the notation of negative 1 to the power of n represents the switching of each value. So it is plus minus plus minus. And so you could also put this into the ratio test, and we are able to obtain that the radius of convergence is pretty much going to infinity. So we can use this definition for any x. So we have already discussed the basics of the trigonometric functions. So I want to give one example of the derivative of the inverse of the trigonometric function. So the example that I'm going to be taking is y equals to the arc sine of x. So from here we could just write this as sine y equals to x. So we can take the derivative with respect to y. We get dx over dy equaling to the cosine of y. Cosine of y could be written as the square root of 1 minus sine squared y, which is x squared, which equals to the dx over dy. So the d of the arc sine is 1 over the square root of 1 minus x squared. And you could also do this for the arc cosine, but instead of doing sine y equals to x, we will be doing cosine y equals to x and then solving for the same thing. So now, after we have already talked about all of this, just by knowing all of these properties, we can start to sketch functions or plotting functions. So there are multiple useful informations that you could get only from the function itself without doing its derivative or doing its integral or whatsoever, or even just trying to figure out each point. Instead, you could actually graph out the entire function just by using these specific points. So first is the is where the y equals to 0 point. So this is where your point touches the x-axis. So the function is intersecting at the x-axis. And sometimes you could solve this pretty easily, since let's take, for example, x squared minus 3x plus 2 over x plus 1 e to the power of negative x over 2. We are able to obtain where would the function go to 0, which is if we actually just see, we can see that e to the power of negative x over 2 couldn't be equal to 0 because it's a power. And then this over x plus 1 couldn't truly make something equal to 0. So it leaves us with the x squared minus 3x plus 2. And it turns out that we could actually factor this out to obtain x equals to 2 as well as 1. So we know where the 0 point is, or the y or the x intersect, which is at 2 as well as x equals to 1. So apart from that, we could also try to find the trend when the x goes to infinity or negative infinity, or maybe even at a divergence point. Like for example in here, if you try to plug in negative 1, the value doesn't exist. But if you try to plug values in between near negative 1, you are able to obtain a value. So that's something important to know as well. So after that, we could also try to figure out what will be the slope at certain points, as well as the local maximum or local minimum. So if we have this function, if you take the derivative with respect to y, you are able to obtain the certain information. If it is equal to 0, you would have a interesting point. So there is something which you call as the maxima, the local maxima, or the local minima, or sometimes even it is like a saddle point. But in here we'll just call it as local maxima and local minima. And so how would you later determine which one is local maxima and which one is local minima? You would need to do the second derivative, which I will later discuss a little bit more. But if the value is less than 0, we know that the slope must be negative. Well, if it is greater than 0, the slope is positive. So slope negative means it's going down, and then slope positive means that it goes up. So you could actually just try to find a value which is easy to compute and then plug it into the derivative. And if you find your value to be negative, it means that it's going down, while if it is greater than 0, it is positive. So you could just pretty much sketch, for example, this function into something like this. So you would have this negative 1, and so in here that's 1, that's 2. So it would be something like this, approximately. So we do see that there is some which is like almost going down, and then there's a point where it turns. And this turning point is where the dy equals to 0. So this is where dy equals to 0. This is also where dy equals to 0, as well as in here. And you could just find this depending on your function. And so another information is the second derivative. So when this is equal to 0, it is sometimes called as the inflection point or the turning point. And so when it is less than 0, what you would have is a local maxima. So the slope goes from positive to negative. So you would have this type of curve. And so if you already figure out where is the local maxima or minima, you could check if it is a local maxima or local minima just by doing the test on the second derivative. And so you could do the same thing here. For if it is greater than 0, you would obtain this local minima. So it goes from negative to positive. So in here we do see at this point the d squared y is less than 0. In here it is the d squared y is greater than 0, and here the d squared y is less than 0. So just by using this, you could actually try to sketch almost any type of function. But there's also a useful tool that you could actually use when you're trying to determine something when it is going to infinity, or when the x goes to infinity, or even the value doesn't even exist. So there's this rule which you call as the L'Hopital's rule. So what L'Hopital's rule truly means is that if you have two functions and then you take the limit, if the limit is at the form of something which is indeterminate, so saying, for example, it's infinity over infinity or 0 over 0, you could use this L'Hopital's rule to determine its limit. So this would be equal to the limit of x going to the same value. So instead, let's just do a. X going to a of the function derivative of a over the g derivative of a. So one example of this is the e to the power of x over x. So let's actually check when x goes to infinity. So what will happen when x goes to infinity? Will it go to 0 or will it go to infinity? So just by using L'Hopital's rule, when x goes to infinity, we would obtain that this will be the same thing as e to the power of x, which is going to infinity. So we could just sketch this out. So it goes something like this. That means that it will be something like that. Give or take, the function is something like that. So it is blowing up towards infinity. And what about if the value is going near 0? Well, only by observing from here, we do see that the value doesn't even exist. But going from the limit as x goes to 0 positive, we are able to see that this will go to a value which is positive. So it's positive 0. That means that it's going to another infinity. So we are able to obtain the state of a function when it goes to a certain value in which it doesn't exist. So it's possible for you to use this L'Hopital's rule. So the proof of L'Hopital's rule pretty much comes from the Taylor series. But in here I would fully discuss how do you actually derive such equation. So this is something very useful for you to use when you're trying to plot functions. Finally, after we have talked about how do you plot functions as well as the L'Hopital's rule, let's try to discuss about the differentials. So differentials are a way for you to express a very small change. So for example, the change of f could be written as df over dx with the change of x, right? Plus a certain error. This is a approximation. But if you take this delta x to be very small, or even the delta f to be very small, you would gain the information that df would be equal to the df over dx times dx. So this is what you call as differentials. So this is very useful. If you're trying to do approximations of value. So maybe sometimes we could just say, if I have a volume to be x cubed, and then if I try to extend this by a certain amount, how much change would it have? So we could just try to express what's the change of volume, which will be the 3x squared dx. So we see here that if I expand it by a small amount dx, it is going to increase by 3x squared times the change. So let's state it is initially 1 meter cubed, and then I'm adding 0.1 meter. So that's the small change of x. So we would know that the change of volume will be about 3 times 0.1 meter cubed, or 0.3 meter cubed. So this is a very useful tool when you're dealing with approximation, as well as the core definition of differential equation, which we'll later discuss at the end of this entire series. So that's all for differential calculus of one variable. So if you want more of these videos, please consider subscribing, as well as liking, and also sharing this video to others who really need to understand the mathematics behind the physics. So thank you very much, and I will see you on the next video.